Hi and welcome everyone. In this lecture, I want to go over basis and dimension of a subspace. So, and what are the conditions for that? So, let's go over the definition first. Given V a vector space, and we have a set of vectors in S, which is a subspace of V. So, now there are two conditions. Number one, if S spans V, S spans V, that means every vector in V can be written as a linear combination of vectors in S. And please watch my last video, I go over the linear combinations. Condition number two, S is linearly independent. So if these two conditions are satisfied, then S is said to be a basis of the vector space V. Let's do a couple of examples so you can see how that works. So the first one in R2. So I put S as set of three vectors in R2, and we can clearly see these have two components, so they are in R2. Now the first question is, does S span R2? If you want to double check that, so you can take, you have to solve the equation AX equals to B, and that must be consistent for any B. So if you want to go directly to the augmented matrix, you can put your vectors as the columns of the matrix A, and I put for B to be C1 and C2, because as I mentioned, it has to be consistent for any B. Now, if I write the first one, you write x plus 2z equals to C1, and for the second one, y plus 3z equals to Z2. And we know here this is an Rref form already. So we have two pivot columns, and the one that's not a pivot is going to be your free variable. So Z is the free variable in this case. You can call Z to be T or S or any number. So then you can isolate X, which is 2Z plus C1, and that's going to be negative 2T plus C1, and same as Y is going to be negative 3T plus C2. So if we write the components X, Y, Z, in this case we get negative 2T plus C1, negative 3T plus C2, and we called Z to be T. As we can see, T and C1 or C2, they can be any numbers. So we have infinite number of solution, no restriction here. So conclusion is S spans V. Next question, is S linearly independent? The answer is no, because as we can see, V3 can be written as 2V1 plus 3V2. Let's check that. And it's very easy to see here, because we can write this column by multiplying the first column by 2 and the second column by 3. And if you double check, you have it. 2 times 1, 0 plus 3 times 0, 1 is going to give you 2, 3. One of the vectors is written as a linear combination of the other two. So then that happens, we know it's linearly dependent. Now, next question, find all the possible bases of S for V. So to do that, you go to your matrix here. So usually it's the Rref, but this is already Rref. So let's see, and find all the linearly independent vectors. So we know that V1 and V2 are linearly independent because none of them is scalar multiple of the other one. So the first base, you can write V1 and V2. Let's check V1 and V3. They are linearly independent because there is no way you can multiply V1 by a number and you can get V3. So they are linearly independent. So the second base, you can write V1 and V3. And finally, you can now check V2 and V3, they are linearly independent. One more time, if you take V2 and multiply it by any number, there's no way you can get V3. So these are three vectors, three bases, because they have the same span of S, but they are linearly independent. So span of S is the same as span of B1, is the same as span of B2, and is the same as span of B3. And B1, B2, B3, they're all linearly independent. Therefore, B1, B2, and 3 can all be a basis of R2. Remember, we don't have to have one basis only. You can have many bases. However, the number of vectors in those bases, they has to be the same. So another question is, what is the dimension of V? And again, note the dimension of V of a vector space is n. So we can call it n, which are the number of vectors in its bases. And that's how you write it. Dimension of V equals to n. Here we have two vectors in each basis, B1, B2, and B3. So the dimension of V is 2. I have a little note for you here. So in R2, the standard basis, so remember that's like a definition, is 1, 0, 0, 1, because any vector in R2 can be written as a linear combination of these two vectors. Basically, standard basis is the simplest basis possible. And I did call that B1. It doesn't make any difference, or you can just say B. In R3, you have 1, 0, 0, 0, 1, 0, and 0, 0, 1, and so on. So these are all the standard bases, because any vector in those vector spaces can be written as a linear combination of the vectors in those bases. Let's go over another example. So again, we are in R2 and I pick three vectors, V1, V2, and V3. The question is S a basis of R2? And we know we have to check two conditions here. If not, find all the possible subset of S that are bases of R2. So these are three vectors in R2. So we know they're going to span R2. So even by looking at two vectors that are linearly independent, the two vectors, so it will. However, they're not linearly dependent. So S is an R2, but has three vectors. Number of vectors is greater than number of dimensions. So S is linearly dependent. So S, in this case, we can't say S is a basis in R2 of R2, or we say S is not a basis of R2. We can stop right there. Now, if you want to find subsets of S that are going to be bases of R2, that's what you can do, is write the matrix and have the columns of that matrix your vectors. And I did that. A is 1, 3, 1, 5, 4, 0. Then find the RREF of A. So to do that, you can do the row operations. As you can see, I did it here, and your RREF is going to be this matrix, and I call that R. So in my lectures, you're going to always see if I say R, that means this is the RREF of the matrix. Now, put both matrices, the original matrix A and its RREF, next to each other. And let's see. When we know for sure one of the vectors can be written as a linear combination of the other one, because we have three vectors in R2, but it's not obvious when you look at A itself. However, when you look at the RREF makes that very easy. We can see clearly that C3 here can be written as 10 times C1 minus 6 times C2, because you have 10 and 6 here. And the good news is the same thing will happen to your original matrix. So you can say if 10 times C1 minus 6 times C2 is C3, then 10 times V1 minus 6 times V2 will be V3 also. And I did the work here to show you 10 times 1, 3 minus 6 times 1, 5 is going to give you 4, 0. So basically will work for the original matrix. Now, if you want to find the basis, just go directly to the Rref and find the linearly independent columns in that matrix. So obviously C1 and C2 are linearly independent because they can't be written as a multiple scalar of each other. So C1 and C2 are linearly independent, then for sure V1 and V2 are going to be linearly independent. So one possible basis is V1 and V2. C1 and C3, so C1 and C3 are linearly independent because if you multiply C1 by any number, you cannot get C3. So therefore V1 and V3 are linearly independent, and it's the same for C2 and C3, so it will be the same for V2 and V3. So that's the third base. So these are all three possible bases. These are all subsets of S, and they can be a basis for R2. So, and we know that the span of S is the same as span of B1, span of B2, and span of B3, and B1, B2, B3 are linearly independent. So they all can be a basis, can be the basis of R2. The dimension, as I mentioned, in each basis, here we have two vectors, so the dimension of V is going to be 2 in this case. Another example, you are given the parametric solutions. That's again a vector set in R3. S and T are real numbers, so we have that. The question is find the basis and find the dimension of W. Solution, always write x, y, z equals to the components given to you in the problem. So we have, then separate s's and t's. So you go the first you have 2s, then you have s. The third component does not have an s, so put 0 instead. Then you have negative t for the first component. The second component does not have a t, so you put 0. And the third component is t, so you put t here. One more time, if you wanna, the way you separate it and you wanna make sure you did that right, do 2s minus t is gonna give you that. S plus 0 is gonna give you s, and 0 plus t is gonna give you t. Factor out s, so you get 2, 1, 0, and factor out t, you get negative 1, 0, 1. So a basis can be 2, 1, 0 and negative 1, 0, 1. Any linear combination of these two vectors will be the basis for the given problem. We do have two vectors in the basis, so the dimension is 2. And there are two bases, two vectors in B. That's how you find the dimension. Another example, here you're given the equation. So again, we are in R3, 5x minus 7y minus 13z is 0, and we are in R3. We all know this is the equation of a plane passing through the origin. So if you want to find the basis for that equation, and we can find the dimension also. So try to find the parametric equations of that. So we know we can say C is S and Y is T, or vice versa. Isolate X from here, put it there too, so you get 7 over 5Y plus 13 over 5Z. And we know Y is T and Z is S, so you just substitute. So then X, Y, Z again, you write the components. Now the parametric components are going to be 7 over 5t plus 13 over 5s, and we said y is t and z is s. Separate them just like the last problem. So this is going to be 7 over 5 t, and there is no t here in the third component, so you put 0 plus 13 over 5s, that comes from here, plus this doesn't have an s, so it's 0, and you put your s here. Factor out t, so you get 7 over 5, 0, 1, factor out s, you get 13 over 5, 0, 1 here. So this is 705, 1, 0 actually. So a basis for that plane can be 7 over 5, 1, 0, or 13 over 5, 0, 1. So what's the meaning? Well, any linear combination, if you take t and s and pick any number multiplied by those, can be a basis for that plane. We have two vectors, and as you know, the dimension will be 2, which is the number of vectors in the basis. I think that's it for this lecture. Please try watch it 2 or 3 times and try some problems on your own. Thank you for watching, and I will see you in my next lecture, in my next video. Have a good one, everyone.